Same type of problem as number 7, it looks like. I'll rewrite it. 10 minus 5s is greater than, we'll distribute that 3s minus 21. We'll collect all the variables onto the same side. I'm going to add 5 to this 5s to this side, and I'll add 5s's to this side. That leaves us with 10 is greater than 8s's minus 21. Okay, getting pretty close. In one move, I can get all the variables and all the constants on the same side. Negative 21 cancels with positive 21. I'll add 21 to this side. This leaves me with 31 is greater than 8s. I will divide each side. So let's see, I'll bring that right up here. Rewrite that. That is 31 is greater than 8s. Divide each side by 8. And that leaves us with 31 eighths is greater than s. 8, 16, 24, 32, so that's almost 4. So you can either come up here and write the fraction 31 over 8, and what that almost, that's like, I don't know what that is, 3.8 maybe. So, and this says s is less than 31 over 8. Remember, you kind of always want to read the inequality starting with the variable so that you make sure that you shade the right way. So by reading this answer from right to left, by reading my answer with the variable, I read s is less than 31 eighths. So I know to shade to the left. S is less than 31 eighths. Let's take a look at 6. Alright, we have another fraction here and kind of a constant out here. We want to get rid of that 6 first. We'll add 6, add 6. That leaves us with b divided by 10 is greater than or equal to 2. Looks like b is being divided by 10, so I will multiply by 10 to cancel those 10s out. If I multiply by 10 on that side, I will do the same thing on this side, which gives b is greater than or equal to, 20. Did the sign flip? No. Why didn't it flip? Because we multiplied each side by a positive number. That does not impact the magnitude of either side of the equation. Therefore, we keep the sign in the same direction. So we'll come up here to our number line. We'll find 20. We'll draw a closed-in circle at 20. We read our equation. It says b is greater than or equal to 20. Therefore, we shade in every value on our number line that's greater than or equal to 20. And that's why we do that closed-in dot, because b could be equal to 20 also. All right, let's get some scroll action going on here. Move down. Wow, that was it. Move down to number 7. A good way to start is by reading the directions. Directions. For each word problem below, A, define the variable. B, write an inequality to represent the situation. And C, use your inequality to solve the problem. So, students, for those of you who enjoy the guess and check method, I hate to inform you of this, but according to these directions, guess and check is not a valid way to solve these word problems. The reason being is because we're testing to see whether or not you understand the concept of reading a word problem and parsing it into an algebraic expression. So let's see what that looks like. So A, we're going to need to define a variable. An apple crate weighs 8 kilograms when empty. An apple weighs about 3 kilograms, 0.3 kilograms, 3/10 of a kilogram. So what? I guess that would be 300 grams. Is that right? For economical shipping, each crate with apples must weigh the crate must weigh at least 50 kilograms. So if we draw a picture of our little crate up here, there's the wheels, there's the axle, I don't know, there's our little crate right here full of apples, little wheelbarrow. So this crate must weigh at least 50 kilograms. It can't weigh any less. It has to weigh 50 kilograms and up. So here's our apple crate. Here's our 50 kilograms. We want to know how many apples should be in each crate to get economical shipping. Okay, so let's come back up here. It weighs 8 kilograms when empty. So this is kind of like our starting value, or this is like our kind of like our fixed our fixed quantity here. An apple weighs about 0.3 kilograms. So we know that each apple weighs 0.3 kilograms. And I'm going to let A represent the apples. So let A equal number of apples. Great, we just did number A. We defined our variable. We defined our variable as A. So B, let's set up this inequality. Well, we drew a little picture up here. We know our crate needs to weigh at least 50 kilos. So our crate, the weight of our crate function is 8 kilograms when it's empty, plus 0.3 kilograms for every apple you load in the crate. And we know that that needs to be greater than or equal to 50 kilograms. So B, write an inequality to represent the situation, and C, solve the inequality. So let's see here. Gotta break out a little calculator here. So first what we'll do is we will subtract 8 from each side. We're subtracting 8 kilograms. That leaves us with 3/10 of a kilogram per apple is greater than or equal to 42. We will divide each side by 0.3 kilograms, divide by 0.3 kilograms. That leaves us with 42 divided by 0.3, which gives us 140. So we need A is greater than or equal to 140. So what this means is that alright, handwriting, let's see what you got. To get economical, I majored in economics, by the way. To get economical shipping terms, we need at least 140 apples. So the trick is really trying to figure out what is going on in terms of our inequality and then relating that to a real-life equation. Okay, let's take a look at number 8. Number 8. All right, the Bugsby Yearbook and Dairy Company charges $500 for a setup. That sounds like a fixed cost to me. And $21 for each yearbook printed. Ah, well, there's your rate. There's your rate of change. So what is the greatest number of books? Okay, greatest number of books that can be printed within the school's budget of $3,000. So it kind of seems that we have $3,000 to work with. And we want to print a bunch of books. I'll just stack up my books here like that. Some little 3D action there. So here's our kind of stack of books. You know, this could be math books, math. This could be history. Yeah. Okay. Oh, they're yearbooks. My fault. So I don't know. 2012, 2011, 2010. So there are yearbooks. And so we want to know what is the greatest number of yearbooks that can be printed within the school's budget. So ask yourself, can we go over the school's budget? No. So we want to see how many books we can print while staying equal to or below $3,000.